I'd like to talk about how to develop clean energy systems. My name is Alex Pavlik. I have an engineering PhD and a professional engineering license. In the 1970s, I was the president of a company that developed a static solar concentrator. I learned a lot about alternate energy, what works, what does not work, and why. Since then, I've been involved in the development of major military systems. I own a variable speed wind turbine patent, and I've written articles about how to develop clean energy systems, the title of this lecture. This talk is organized around four themes. The first theme is strategy. If we have a clear strategic goal, we can use that goal as the basis for making decisions. The second theme is systems. We need systems that are reliable, clean, and cheap. We simply can't plug together a bunch of components and expect them to work together as an efficient unit. The third major theme is scenarios. A strategic scenario is a simple architectural model that characterizes the cost and performance of a particular system concept. The fourth theme is management innovation. To build a public mandate, we need a clear understanding of roles and responsibilities, and we need to innovate some traditional system engineering management tools. So let's get started. Let's start by talking about the importance of having a strategic goal. Engineers have a broad spectrum of design tools available depending on how well we can define a goal. At one end of the spectrum, we have rational planning. Rational planning requires a clear and stable goal, a strategic goal. All decisions are based on achieving that goal. At the other end of the spectrum, we have evolutionary development. Evolution has no goal. There is no overarching purpose. Decisions are made through local optimization, natural selection. In between the two extremes, we have various levels of agile development, depending on the clarity of the goal. Agile development is a way to develop systems when the goal is fuzzy or changing, as is often the case with consumer products. Decisions are based on market feedback. We seem to be developing clean energy systems by looking at what exists and asking how we can reduce emissions today. The advantage of this approach is quick, immediate returns. There are many ways to reduce carbon emissions now. The disadvantage of this approach is confusion. Without the clarity of a goal, we can make big mistakes. We pursue technologies that are in conflict with the strategic goal. Big emission reductions will be very difficult to achieve. Okay, let's talk about the strategic goal. First, I'm using the term strategic goal in the military sense to designate a final objective. A good strategic goal defines end state performance. Once we achieve the goal, we're done. There's nothing more to do. The mission is accomplished. Now, the classic planning sequence consists of several sequential stages. First, we set the goal, the objective, the purpose. Second, we explore alternative solutions. This is classic scenario development, a factual analysis. Third, we choose a direction. This is a value judgment, a management decision based on feasible alternatives. Fourth, we develop a plan to how to get there from here. Now, it's important to note that strategic planning is diametrically opposed to evolution. In evolution, we start from where we are and we look for ways to make progress, to move forward. In planning, in contrast, starts from where we want to be. We choose an end state, then we figure out how to get there from here. Now, in preparation for the 2009 Copenhagen Conference, President Obama articulated a strategic goal. He said we want an 83% reduction in CO2 emissions below 2005 levels by 2050. That's a very good strategic goal. First, it's an end state performance goal. It's not a mandated solution like 20% renewables. Second, without quibbling about the numbers, it is saying that we want really big emission reductions in a 2050 time frame. This could be justified by environmental concerns, health, national security, as well as concerns over CO2-induced global warming. Claiming that the goal is impossible or too expensive is an unsubstantiated opinion because we have not yet developed the scenarios. So, accepting that goal, how would we proceed? The first step is to decompose the requirement. What does it mean to reduce CO2 emissions by 83%? This chart is taken from a paper I published in the American Scientist several months ago. The first three bars divide actual 2005 CO2 emissions into three categories: generation of electricity, motor vehicle fuels, and everything else. The fourth red bar shows the 2050 emission goal. The everything else bar includes natural gas for space heating, the green hash with the X, easily replaced by electric heat pumps. The remainder of the everything else bar includes difficult to replace fossil fuel applications like chemical industry feedstocks, coke for steel, jet fuel. The remainder of the everything else bar is about the same as the 17% goal. The white area is about the same as the 17% goal. The main conclusion from this chart is that an 83% reduction in CO2 emissions is feasible if we can achieve a zero-carbon electric power grid and a zero-carbon motor vehicle fuel. A natural solution is an electricity-based motor vehicle fuel. The key to big emission reductions is a zero-carbon electric power grid. The next step in strategic planning is scenario development. A scenario is an architectural model of an end-state system configuration. Its purpose is to estimate cost and performance. Scenarios are based on known technologies. It includes data-based learning curves for cost and performance improvements, but it cannot assume system breakthroughs. Scenarios ignore current policy and legacy system constraints. We start with a blank sheet of paper. This is an enormous simplification. Policy and plans for how to get there from here comes later. Scenarios capture only enough detail to estimate system cost and performance. They must capture structural system relationships. This is the architecture. But too much detail too soon obscures system structure and introduces confusion. Scenarios provide a factual definition of the feasibility of various choices. Scenarios are followed by design reviews, management decisions, then policy and plans. On the right, we have a partial list of system scenarios. Let's look briefly at nuclear power scenarios. France has an electric power grid that is 90% carbon-free. That's 90% carbon-free today. It is 80% nuclear, 10% hydro, 10% fossil fuel. The price of electricity in France is 4.75 euro cents per kilowatt hour before taxes. That's the cheapest price in Europe. It took France 37 years to build this system from 0 to 80% nuclear. They had a national commitment to do so. The reason nuclear power appears expensive in the United States is because of the high cost of capital. This is the interest rate on the money spent to build the reactor. In the U.S., nuclear power cost is a political as well as a technical issue. In the U.S., nuclear power today is 17% of total power production. Given the French experience, there's no reason why the U.S. can't go from 17% to 80% nuclear over the next 40 years if we chose to do so. Small modular reactors are changing the game. These reactors are factory-built, truck transportable, and lower cost. There are many variations. Most employ the same single-pass light water fuel cycle as the large site-built reactors. Smaller size means lower risk, more insurable, and scenarios are needed to quantify cost comparison and identify constraints. Nuclear power is a feasible zero-carbon solution if we choose to embrace it. Intermittent generators have system issues that are generally ignored. By intermittent generators, I'm referring to wind, solar, waves, tides. System scenarios will show a deep conflict between intermittency and the system requirement to deliver energy on demand. Intermittent generators cannot stand alone. They increase net load fluctuations, conflicting with smart grid efforts to level load. They have little or no firm capacity. The free lunch model, where intermittent generator is plugged into the grid and the grid takes care of intermittency, simply does not scale to larger systems. Without good system design, intermittent generators can block the deployment of baseload generators like nuclear power. We can use system scenarios to find durable niches for intermittent generators. The approach would be to partition the grid into standalone subsystems. A subsystem would consist of the intermittent generator plus something else, like wind plus hydro. Each subsystem meets overall system requirements for reliable, clean, and cheap. Let's talk about the management innovations that are needed, starting with the kinds of problems we are confronted with when developing clean systems. clean energy systems. This task falls within the class of what the literature calls wicked problems. Wicked problems have more than one feasible solution. Both technology judgments and value judgments are important in finding a satisfactory solution. A classic wicked problem is the client who wants a dream house. Only the client can decide what constitutes a satisfactory dream house. The client often starts with vague or unrealistic ideas, so they hire an architect to discover an affordable concept, and later a builder to convert the plans into reality. There are three primary roles here: value judgments, technology judgments, and coordination. For satisfactory solutions, each role must be separate and distinct. There should be no overlap. There should be a healthy tension between these roles. So how do these roles map into the task of developing clean energy systems? My suggestions are on the right. The architect is the executive, the president, state governors, Department of Energy at the executive level. The architect is responsible for enforcing good process and best practice, particularly the goal, open design reviews, and high-level system development plans. The engineer consists of national laboratories, various experts, laboratories, and manufacturers. They're responsible for research, development, and technical analysis. Engineers have a healthy bias towards their specialty. The client consists of Congress and state legislatures representing the general public and special interest groups. Okay, let's talk for a moment about the risk from changing technology. Technology change is managed using phase development. Engineers typically partition development programs into a sequence of phases. Phases are separated by design reviews and management decision milestones. Design reviews are an objective determination of fact. Management decision milestones decide what to do next, given the factual status of the program, and systems are decomposed into a nested set of many such plans. It is the architect's responsibility to set up and enforce this practice. Design reviews are an objective assessment of fact. The design review determines if the development progress is consistent with requirements, system requirements. The traditional format is an orchestrated closed session between the client and the contractor. The developers are cross-examined by an expert design review board. In clean energy, a design review with an open format would encourage buy-in by multiple stakeholders. A design review is followed by client choice, a decision to proceed, redirect, keep development in an earlier stage, or to terminate a particular effort. One of the serious difficulties associated with clean energy development today is that technologies like wind power are being transitioned from demonstration to production without a responsible design review. In conclusion, we have an excellent strategic goal, President Obama's Copenhagen goal. To reach this goal, we will need an electric power grid and a motor vehicle fuel that are essentially zero carbon. Rational planning uses this strategic goal to drive decision-making. Planning focuses resources and avoids big mistakes. Planning has a long history of producing elegant system designs. Cost and performance need to be evaluated at the system level. Reliable, clean, and cheap is a system requirement. How all these pieces fit together to function as a unit is very important and cannot be ignored. The next step should be strategic scenarios, the architecture of various end-state solutions. Scenarios will clarify feasible choices, technology needs. We should also initiate phase development to manage technology change. We should also initiate open design reviews to provide objective independent assessment of fact and encourage buy-in by a broad range of stakeholders. We know how to develop reliable, cheap, clean energy systems. The challenge is simply getting our act together.